In the last section of Chapter 10, we will be looking at the idea of being able to predict the shape, the three-dimensional shape of a molecule based on the two-dimensional Lewis structure, and then we'll talk about the ideas of electronegativity and polarity. Now, when we're looking at the prediction of the shape of a molecule, we're going to start with a Lewis structure, and then we're going to apply something known as the valence shell electron pair repulsion theory, also abbreviated as VSEPR or VESPR. You'll hear people call it VESPR, and I know it doesn't really match up to the letters, but if you hear somebody talking about VESPR theory, that's what they're talking about. It can be used to predict a three-dimensional shape of a molecule, and it's based on the idea that all of the electron groups, whether they be lone pairs, single bonds, multiple bonds, electrons are going to repel each other, like charges repel. So the repulsion between the negative charges of the electron groups on a central atom are going to determine the geometry of the molecule. It's all based on whatever atom is in the center of the structure you're looking at. You're going to look at what's attached to it. So if we look at an example of that, we start with carbon dioxide, and we already determined the Lewis structure in the earlier section for carbon dioxide. Looks like this. The geometry of the carbon dioxide is going to be determined by the repulsion between the two electron groups on the central carbon atom, where the electron groups are the two double bonds. Okay, so when we talk about an electron group, an electron group can consist of a lone pair of electrons. A lone pair of electrons counts as one electron group. A single bond would count as one electron group. A double bond would count as one electron group. And a triple bond would count as one electron group. So each one of those counts as only one electron group. So this would be electron group number 1. This would be electron group number 2. Now, those two sets of electrons, those two electron groups, are going to push each other as far away as possible. Since there are only two of them, how do two things get as far apart from each other as possible? Well, they line themselves up on either side, diametrically opposed on that central atom, resulting in a bond angle of 180 degrees. That's as far apart as they could get. If either one of them moves up or down a little bit in any direction, it's going to get closer to that other set of bonds. Okay, so the bond angle would be 180 degrees, which is a straight line. That is known as a linear geometry. So the shape of a carbon dioxide molecule is linear, just like you would draw it on paper. So here's a three-dimensional representation. It would just be a central atom and then two atoms on either side of it. Easy when it's linear. It's just like it's laying in the plane of the paper. Right, now let's look at something that's a little more complicated. Let's look at H2CO. Now, if I work out the Lewis structure for this, and this is formaldehyde, by the way, the Lewis structure would look like this. Now, this molecule has 3 electron groups. A single bond here, there's 1. Single bond here, there's number 2. And a double bond here. Double bond counts as only 1, so that's your 3rd electron group. Now, if you think about it, how can 3 items get as far away from each other as possible? Well, they're going to arrange themselves, again, in the plane of the paper. They're going to lay flat in a plane, okay, just like they're laying flat on a piece of paper, and they're going to push themselves apart until there's 120 degrees between each of the atoms. Okay, now if you picture what we have here, this is forming a triangle, okay? So we call that trigonal, and because it's still a fairly two-dimensional structure, it's still lying in a plane, we call it planar. So this is known as a trigonal planar geometry, and the angles between any given set of atoms is 120 degrees. Because again, if I try to bring it out of the plane of the paper, if I, for instance, take the oxygen and try to lift it up, it may get further away on the other side, but now it's getting closer. There's no way for it to get any further away from those other two atoms than lying in that direction. Now, when we say that we have 180 degrees and we have 120 degrees, be aware that the angles that we predict for things such as formaldehyde are approximate. And this is because if we look at that structure, so we've got a double bond to an oxygen and a single bond, to each of the hydrogens here, the carbon to oxygen double bond has a higher electron density than the carbon to hydrogen single bonds. So because there are more electrons, it's like, if you think of it in terms of magnets, it's a slightly stronger magnet, so it's going to push a little harder. So the bond angle between the hydrogen to hydrogen, actually, because these aren't as strong, they're being squished a little more by that oxygen double bond, if you will. It's actually not quite 120, it's about 116 degrees. And this, because this one's pushing a little bit harder, that oxygen's pushing a little bit harder on everything, these are actually more like 122. But for all intents and purposes, we can say it's about 120 degrees. There's certainly a significant difference between 120 degrees and 180 degrees, or the next angle that we're going to see in the next structure. So if you said 120, if you're 122 or 116, that's splitting hairs at that point. All right, so the next one we want to look at, what happens, we've looked at 2 electron groups and 3 electron groups. What happens if we have 4 electron groups around a central atom? Okay, so the example they're showing is CH4, methane. Now, when we look at this, 4 electron groups, 4 single bonds in there, I could draw it two-dimensionally on paper the way they're showing in this structure, and it looks like, oh, okay, it's going to lay flat in the piece of paper and there's 90 degrees in between each of those. But if you think of it, instead of thinking of it two-dimensionally on paper, think if you had 4 balloons and you wanted to tie the 4 balloons together at their base. So you blow up a balloon, you tie it shut, and it's got that little knot. Okay, that kind of represents the shape of these things when they come together. There's a narrowing where they're going to bond and attach, and then all the electrons kind of get pushed out to the outside. If you tie 4 balloons together, are you going to be able to make those 4 balloons lay flat? Well, you might be able to if you force it, but they're not real happy about it. What's more likely to happen? What's more likely to happen is you can tie 3 of them together and get a nice triangular structure, and then you stick one in on top. And that's going to push the 3 on the bottom down a little bit. And that's exactly what happens. So it's sort of like you take that triangular arrangement. Okay, so if I had an H, so if I had something like I looked at before with the trigonal planar, and I bring one from the top down. So imagine I have another hydrogen, and I'm coming straight in at it onto the screen. And I'm going to lay it right over the top of that and attach it to that carbon. Well, it'll attach to that carbon, but then these other 3 are going to get pushed away. So if you can imagine, they're going back into the screen while that other hydrogen is laying on top of the screen. And it's going to create what's known as a tetrahedral structure or tetrahedral geometry. Now, with tetrahedral, bond angles, if you think about how this is arranged, so here's my carbon in the middle and the hydrogens all get pushed as far away from each other as they can, that angle then, dividing 360 up, okay, dividing that whole sphere up, what's going to happen is I've got 109.5 between each of those. Okay, so a tetrahedron is a geometric shape that has 4 triangular faces. That's what we're looking at, a tetrahedron. It's a tetrahedral geometry. Okay, so what they're showing here is what's known as a ball and stick model. Okay, and I'm sorry, it says left and right. The ball, they don't really have a ball and stick or a space filling model here. I'm sorry, the wording is incorrect on this. They don't have a space filling model in here. It is simply a ball and stick. There is no space filling model on this one. So look in your book for the space filling model. The space filling model more closely portrays molecules, but it's hard to see where the attachments are. So ball and stick models tend to be used in order to illustrate the geometry more clearly. Okay, so my apology, look for the space filling model on the in the book in that chapter. All right, so here's your space-filling model right here. You can see it. So you can see with the space-filling model, that's more realistic of the overlap of the electron orbitals, what you would really, quote, see if you could see the molecule. But you can see that in the ball and stick model, it is much easier to kind of clarify that structure and to see what's going on there. All right, so what's happening is you've got the mutual repulsion of all 4 electron groups that's causing this shape. Allows maximum separation of the groups. They're pushed as far away from each other as they can get. So we write the structure on the paper. It looks like it should be maybe square planar. It looks like, if I drew lines around it, I could make a square. It's lying flat on a sheet of paper, 90-degree angles, but that is not the reality. So you've got to be careful to not think of Lewis structures in terms of their 2-dimensional structure on paper. If you have a hard time seeing these structures in 3 dimensions, there are modeling kits you can get that can help you put them together and get an image of what they will look like in 3-dimensional space. If you're interested in looking at those kits, we do have them in the classrooms and the labs at OTC where you can borrow them and look at them. If you want a set for home, let me know and I can recommend some places where you could buy your own kit or ways that you possibly could make your own kit. All right, now in all of the previous cases, we were looking at shapes of molecules that had only bonded pairs, bonded electrons. What happens if you have a molecule that has a lone pair of electrons on the central atom? Okay, so every other central atom we looked at, it had nothing but bonds. Let's look at ammonia. So if we look at the Lewis structure for ammonia, it has 4 electron groups. Okay, so we've got 1 lone pair here, there's an electron group. Okay, there's number 1, and then we have number 2 is this single bond, number 3 is this single bond, number 4 is that single bond. If we look at the electrons, the geometry with all the electrons, known as the electron geometry, is tetrahedral, just like we looked at in methane. Okay. But if we look at what's known as the molecular geometry, which is just the arrangement of the atoms. So when you're talking electron geometry, you're talking everything that's in the molecule attached to the central atom. If we are talking molecular geometry, we are talking about lone pairs being invisible and only being able to see atoms. And now if that were the case, if I look right here, here's the lone pair. It's still affecting the shape. It's still part of the molecule. It's up here pushing down on these hydrogens, so it still gives that tetrahedral arrangement, but I can't see them. They're invisible. All I can see is this ball and stick model. So when I take it down to the ball and stick model, what do I see? Well, what I'm seeing is that I now have a trigonal pyramid. I've taken the top off of my tetrahedral pyramid, so now instead of having 4 sides, it's only got 3 sides. Here's one of the faces here, here's one of the faces here, and then there's one in the back. Okay, I mean, it still has a bottom to it, sort of like the tetrahedral, but there's only 3 atoms bonded there. So and it's not lying flat anymore because that lone pair is pushing down. So this is known as a trigonal pyramidal structure, or pyramidal, whichever way you prefer to say it. Most chemists will say pyramidal. Okay. So the bond angles in ammonia are actually a few degrees smaller than ideal tetrahedral angles just because of that lone pair pushing down a little bit harder. If I look at a water molecule, now I have 2 lone pairs on the central atom. Okay, so here's one, there's 1 electron pair, electron group, there's 2, here's 3, and here's 4. I still have 4 electron groups. Okay, so if I put it into the electron geometry, I'm looking at everything on there. Here's oxygen, I've got a hydrogen on one corner of my pyramid, a hydrogen on the other corner, I've got a lone pair at one end and a lone pair at the top here. All right, so again, that whole thing's tetrahedral. Those lone pairs still come into play and they still affect the shape of it. But if I can only see the atoms again, if those lone pairs are invisible, what does this look like? Well, it looks bent. So if I'm looking at this two-dimensionally on paper, it looks like, oh, well, that's linear. It's got to be linear. They're straight across from each other, but they're really not because the lone pairs of electrons have shoved them away. And so what you end up getting is kind of this V structure. So if I put my oxygen here, hydrogen and hydrogen. Okay, so the way they have this angle, this is actually closer to you, the oxygen, and each of these hydrogens is kind of pushing away from you. Imagine them traveling away from you. So I end up getting this bent structure. That is the molecular geometry for water. So it can have a different molecular geometry from the electron geometry if there are lone pairs on the central atom. If I have no lone pairs, then the molecular geometry is the same as the electron geometry. Table 10.1 in your book has some basic examples, and it lists the electron groups. So when you count electron groups, okay, keep in mind those are only on the central atom. If you have 2 electron groups, those are almost always going to be bonding groups. Otherwise, you just have something like cyanide, where there's just 2 atoms. So if you have 2 electron groups, it's going to be 2 bonding groups. You're not going to have lone pairs in that case, and your electron geometry is linear. Your molecular geometry is linear. It's the same. And then you've got your angles between the groups given right here. All right, so notice that there's only one case for 2 electron groups right there. And here's an example of it. Now, 3 electron groups, I can have 2 different situations. I'm going to draw a line here. I can either have all 3 as bonding groups and 0 lone pairs, in which case the electron geometry is trigonal planar, and the molecular geometry is trigonal planar. If I do not have lone pairs, those 2 are always the same, electron and molecular geometry. But I can have a lone pair, in which case, notice now, it doesn't matter to the electron geometry how many lone pairs I have. Electron geometry is only based on number of electron groups. 3 electron groups, electron geometry is always trigonal planar. But the molecular geometry will change. Okay, now, with 1 lone pair, this is bent instead of being trigonal planar. And if I have 4 electron groups, okay, I can have the case of 0 lone pairs, 1 lone pair, or 2 lone pairs. Notice they are all tetrahedral in their electron geometry, but I go from a tetrahedral molecular geometry to a trigonal pyramidal to a bent. Okay, so it's worth taking some time to look at this table and study it and get a feeling for those, because you need to be able to take a Lewis structure and then make a prediction on electron geometry and molecular geometry, on bond angles, on number of bonding groups and lone pairs. So this table can actually expand out. You can have more than 4 electron groups for those atoms that we talked about that are the exception to the octet rule, that have an expanded octet. So if you ever go looking on the internet or in other books, you will probably see a much larger table than this. And you can imagine, you notice that with 2 groups, there's only 1 case. With 3 groups, there's 2 cases. With 4 groups, there's 3 cases. That continues on. If you have 5 electron groups, there's 4 different scenarios. If you have 6 electron groups, there's 5 different scenarios. So it gets pretty hairy as you keep going. But as we said, we're not going to look beyond the tetrahedral. That's going to be our cutoff point. We want to know it up to that point. All right, so just a rundown again, how to predict geometry using VSEPR theory. First step, draw a correct Lewis structure for the molecule. That's key. If you don't have a good Lewis structure, you're not going to get the right geometry for your molecule. Okay. Determine the total number of electron groups around the central atom, where a group is either a lone pair, a single bond, a double bond, or a triple bond. Each one of those counts as 1. Determine the number of bonding groups versus lone pairs. Okay, so lone pair is in a case by itself. Bonding groups is single, double, and triple bonds that are around the central atom. And then refer to table 10.1 until you kind of get the hang of it, until you can look at it and see them. So you can look at table 10.1 to determine the electron geometry and molecular geometry. Now, do know that eventually you should be able to say what that is without referring back to the table. But starting out here, go ahead and use that table. as much as you need to. We will kind of evaluate where we are before we get to the next test on that. Now, how do you then represent a molecular geometry on paper if it is not two-dimensional? There are standards that chemists use to denote three-dimensional structures in two-dimensional space. So when you're looking at a structure, and this, again, you will see all the time in organic chemistry, they have what they call a projection molecule. A projection molecule is projecting the spatial relationship of atoms within the molecule. So if you see a straight line, that means that whatever bond you're looking at lies in the plane of the paper. So it would be, if it were in reality, it would just be laying there on the paper. If you see a series of hashed lines, those are bonds that project into the paper, so they're moving away from you. So if you imagine that you took your bond and you pushed it, you left one end of it on the paper and pushed the other end away from you, that's what that's representing. So the point would be lying on the paper. This point out here at the end of the hash lines is behind the paper. And then a wedge is just the opposite. The point of it is lying on the paper. This end of the wedge is coming out towards you. It's projecting out of the paper as though you were taking it and pulling one end of the bond toward you. And here's some examples of how those would look, drawing those. So these are the major molecular geometries that are used in the book, shown using that notation. So linear is all within the plane of the paper. It's just lying flat. Trigonal, planar, and bent. Those three are easy because they're pretty much two-dimensional. They just lie flat in the plane of the paper. Now tetrahedral, what you would show, okay, so in this case, here's your central atom, and then two of them are lying flat in the paper. So this would be in two-dimensional space, and then you've got one molecule that's pointing away from you, that's behind the plane of the paper. This one, not quite sure why I did that. This one is coming out toward you. Okay, so that's pointing out of the paper. It's in front of the paper. Same thing with this one. In this case, this X is behind the paper, this X is in front of the paper, and this one is lying on the paper. Okay, so you can kind of picture them three-dimensionally that way. So this is definitely a skill that takes a lot of practice and development, but I would encourage you to really practice this and get used to looking at these, because again, when you hit organic chemistry, you'll be seeing these projections quite a bit more, because these structures, particularly the tetrahedral structure, becomes very important to looking at these molecules and deciding the differences between organic molecules. Sometimes the main difference is the geometry of the molecule, and also being able to understand how they're going to bond with other things. Okay, so one example of how molecular shape makes a difference, it has nothing to do with the actual chemical components, but just the shape of it, is listed in one of the chemistry and health boxes in your book, and it talks about artificial sweeteners, and it's really interesting. If you look at an artificial sweetener, such as aspartame, we know that they taste sweet. Now there's, a lot of people get a little bit of aftertaste with it or whatever, but they're very sweet tasting, but they have few to no calories. So you can eat these and not gain weight from them. So taste and caloric value are two separate properties of foods. So we can use that to our advantage. We can find foods that our bodies don't recognize as calories, but still have this property of taste. Okay, so if we look at sugar, table sugar, sucrose, and we look at how our body uses that, well, it's an oxidation reaction to carbon dioxide and water. Now, this should look familiar to you. We have something with carbon, hydrogen, and oxygen as a fuel, mixing with oxygen to form carbon dioxide and water. This looks very similar to a combustion. And actually, other than the fact that it's a slow burn that happens in your body instead of a very rapid one, it is essentially a combustion reaction. This is how our body is utilizing fuel, the same way that a fire utilizes wood for fuel. And you can see here the enthalpy is a negative 5,644 kilojoules. Okay, that relates to the number of calories that are in there. Now, if we look at artificial sweeteners, say saccharin, those don't get metabolized by our body. So you consume them, they taste sweet, but they pass through the body completely unchanged and not, too much information, but they come out pretty much the same way as they went in. So they don't have any caloric value. In order to have a caloric value, the body has to recognize that molecule as a fuel, and it has to carry out this oxidation in order to release the energy from that fuel. Okay, or you can have artificial sweeteners such as aspartame that they do get metabolized by the body. They do undergo that, but it's at a very slow rate. You get very little enthalpy from those, so it's a much lower caloric content compared to sucrose. Okay, so what is it about those molecules that allow them to taste sweet but not act as a fuel? Well, if you look at the structure of the tongue, we have specialized cells that are basically little molecular detectors. So we actually, if you look at all the instrumentation a lab has, we actually are very finely tuned instruments in that respect. We have wonderful detectors for taste, for smell, for sight, for touch. This just happens to be for taste. And the way that our tongue figures out what something tastes like is based on the shape of the molecule. So if you look at the surface of a taste cell, there are specialized protein molecules that are called taste receptors. You've probably heard of those. And if you can taste a molecule, it's because the shape of that molecule kind of locks into a special pocket on that receptor protein. It's called an active site. And that active site, when it gets the right shape, it's like, if you are trying to put blocks in. So you've got a round hole that's an active site. You need a round peg to put in that hole. When that happens, you taste it as sweet. Okay, so artificial sweeteners work that way because they just happen to have a shape in them that fits into that receptor pocket, and it triggers that sensation of sweet. Okay, it's the same thing that sucrose does. So sucrose has the round peg somewhere. Aspartame, saccharin have that round peg somewhere. And so they bind to the active site in the protein, and they even bind more strongly than sugar. So that's why we say they taste sweeter than sugar, because they bind more tightly than sugar, and they fire that activation, so you get more of a sensation of sweet. It actually takes 200 times the amount of sucrose to trigger the same amount of nerve transmission as aspartame. So you only need 1/200th the amount of aspartame to get the same sensation of sweetness. Okay, but now that's the only thing that the aspartame and saccharin have, that it binds to that receptor site, it gives you that sensation of sweet, but then once you consume that and it gets into the body, it's not a fuel. If you look at the molecule, it's not going to react with oxygen, or it's going to react very little with oxygen, and it's not going to give you the same energy. Okay, so that is how those work. It's really interesting. Now, the last part of this chapter we want to look at is the idea of electronegativity and polarity, or why oil and water don't mix. So if you put oil and water in a container and you shake it up, you might see some little beads of oil in the water and vice versa, but eventually if you let it sit and settle out, they separate into a layer of oil on the top and a layer of water on the bottom. Okay, so why is that happening on a molecular level, on a chemistry level? Well, there's something about the molecules, in particular the water molecules, that cause them to kind of bunch together in one region. They're selective, and they don't like the oil molecules, so they expel the oil molecules into a separate region. And because the oil is less dense, that usually tends to be on top of the water. So we can explain why this is looking at the Lewis structure for water. Okay, so here it is again. We've already drawn it several times. So we know that there are single bonds between oxygen and hydrogen, and they each consist of one electron pair, which is 2 electrons being shared. And we also have 2 lone pairs of electrons on the oxygen. Now, the oxygen and the hydrogen have each donated 1 electron to the pair. And up to this point, we've just assumed that they're sharing equally. But you know what? They don't really share equally. This is kind of like Big Brother, who had lots of electrons to start with, and Little Brother, who only had 1. And Big Brother's a little bit stronger, and he's maybe going to take a little bit bigger piece of the pie. Okay, the oxygen atom actually takes more than half of that electron pair. Not so much that the hydrogen doesn't really still consider itself as having a duet, but those electrons are closer to the oxygen than they are to the hydrogen. Okay, the reason for that is the electronegativity difference between oxygen and hydrogen. So the ability of an element to attract electrons to itself within a covalent bond is known as electronegativity. Now notice we're only talking about covalent bonds here. And this is where, if we'll look at the trend of it, but it starts over at fluorine and drops as you go down and left. Oxygen is closer to fluorine than hydrogen. Oxygen is more electronegative than hydrogen, which means on average that shared electrons between those two are more likely to be found near the oxygen atom than near the hydrogen atom. So what happens is if we can represent the density of the electrons, remember we talked about orbitals, and we talked about representing shapes of orbitals and the electron densities. So if I could draw the probability of an electron being anywhere around one of those two atoms in a bond, this is what it would look like. I'm going to have more electrons around the oxygen down here. So I'm going to see kind of a bigger circle down here. The hydrogen, you notice, they hang around the hydrogen, but then it kind of gets stretched and pulled out toward the oxygen. And when this happens, you can see there's a higher density of electrons around the oxygen. Okay, we represent that by this symbol known as delta minus. Delta minus indicates a partial negative charge. That means that it's not a true charge like an ion, but there's kind of a net movement of electrons at this end. And then we have this symbol, which is delta plus. It indicates a partial positive charge. There's a little bit less of an electron density around the hydrogen. Now, when this happens, when you have an uneven sharing of electrons around a bond, a covalent bond, that is known as a dipole moment. It's a separation of the charge within the bond. So it's not an equal bond. When you have a dipole moment, this is known as a polar covalent bond. So you can have polar covalent bonds and you can have non-polar covalent bonds where electrons are getting shared evenly, and then you have ionic bonds. Now, when you have a polar covalent bond, the magnitude or the size of the dipole moment, so the difference between the electronegativity in the two, the polarity of the bond, is dependent on the actual numerical difference between them. Okay, so if I know the electronegativity of one atom and the electronegativity of the other, the bigger the difference between those, the bigger the dipole moment, the more polar the bond. Okay, the length of the bond also has a little bit to do with that. So if you have, for any given bond length, for a fixed bond length, the greater the electronegativity difference, the greater the dipole moment. Okay, so there's your takeaway right there. All right, so how do we assign that? Well, Linus Pauling invented an electronegativity scale. He just arbitrarily, once he determined that fluorine was the most electronegative, he decided to set its value at 4. There's not necessarily a reason, I mean, there's historical reasons for that, but it's not an empirically calculated value. This was an arbitrary value that he set. Okay, and then he computed all the other values relative to that. So every electronegativity is relative to fluorine. Okay. So if we look at a table of electronegativities where 4 is the strongest electronegativity you can have, and down here at about 0.7 is about the weakest, okay, we can see that the highest electronegativity is fluorine. It's up here in the upper right corner of the periodic table. And generally speaking, with some exceptions, it tends to drop as you move to the left and drop as you move down. But you can look at these relative one to the other. Okay, so if you have a table of electronegativities, as you see here, you can use these values to calculate the strength of a bond. All right, so let's look at some of these cases. Let's say we have two elements that have identical electronegativities. Now, it's easy to tell if the atoms are the same, that they're going to share electrons equally. So, for example, we have the chlorine diatomic molecule. The two chlorine atoms are going to share their electrons equally. So this is a pure covalent bond. That's all it is. It's not a dipole at all. So we would call this a nonpolar covalent bond. It's a nonpolar molecule. There's no net positive or net negative end to the molecule. And going back just for a second, it wouldn't have to be just like chlorine with chlorine, 3 and 3. If I had any two atoms that had the same, so for example, if I had carbon bonded to sulfur, they are both 2.5. There's no difference in their electronegativities. Neither one of them is going to draw electrons to itself more strongly than the other, and so that would also be a nonpolar molecule, that bond. Now, what if I have a large difference, a really, really big difference between the two, such as what we normally get with a metal and a nonmetal? Well, when you have a really big electronegativity difference, the one that's more electronegative is usually so strong, it just rips the electron off the other one. Okay, there's a complete transfer, and this is when we get an ionic bond. Okay, so we've got nonpolar bonds and ionic bond, but then you've got this huge middle-of-the-road area where you've got an intermediate electronegativity difference. Okay, and when we say intermediate, what do we mean? What's a numerical value? We'll look at that in a minute, but somewhere between strong enough to rip an electron off or let's share equally. So if we look at hydrogen fluoride, the electrons are being shared between the two, but fluorine's very electronegative. It's not electronegative enough to completely rip the electron away from hydrogen, doesn't make an ion out of it, but it shares it, okay? It doesn't share it very equally. You can see here the density around the fluorine is very large, the density around the hydrogen is very small, so we end up with more electrons at this end, partial negative, fewer at this end, partial positive. This is what is known as a polar covalent molecule, a polar covalent bond. All right, so what's the numerical value? Now, degree of bond polarity is continuous. There isn't really a hard cutoff to say, oh, this is where nonpolar ends and polar begins, or this is where polar covalent ends and ionic begins. There's a continuum. You can have something that's kind of on the borderline between polar covalent and ionic. It's all a degree of relativity, but relative guidelines in general, we say that when the electronegativity difference is between 0 and 0.4, this is what we call a pure covalent bond, a nonpolar bond. If it's somewhere between a difference of about 0.4 and 2, this tends to be a polar bond, a polar covalent bond. If it is greater than 2 or greater, tends to be an ionic bond, such as sodium chloride. Those are your metal nonmetals. Again, you know, where that hard cutoff is, there's no hard cutoff. It's a continuum. So really what you're doing is just comparing the strength of one bond to the other. Does it have a dipole moment? If it's right on that borderline, you know, you could argue either way. But certainly if you've got something that has an electronegativity difference of 1, it's smack in the middle, that's a polar covalent bond. Now, we're looking at the polarity of a bond, and you can have more than one bond in a molecule. So you can assign a polarity to each bond within a molecule, but then can you designate a polarity for the entire molecule? So if I have one or more polar bonds in a molecule, do I then have a polar molecule? Do polar bonds equal polar molecule? And the answer is no. Okay. In order to have a polar molecule, I have to have polar bonds which are not even. Okay, so a polar molecule is going to be one in which the polar bonds form a net dipole moment for the whole molecule. They don't cancel each other. So we can almost think of it as a tug of war. So I've got a central atom, and I have atoms around the outside that are pulling on it. Do they all pull equally? If they do not have a net dipole and it's nonpolar. If they don't, if some of the bonds are more polar than others or stronger than others, then I get a net dipole and I have a polar molecule. So if we look, for example, at carbon dioxide. Now, if I'm looking just at this bond, I'm looking at the double bond between carbon and oxygen. Now, that bond is polar because if I look at the difference in the electronegativity between oxygen and carbon, it's 1. As I said, that's between 0.4 and 2, smack in the middle. That's definitely a polar bond. This one is the same thing. That's a polar bond. But now imagine I have a polar bond with a strength of 1 over here, and I have a polar bond with a strength of 1 over here. This is a linear molecule. They're going to pull on each other equally. This one's going to pull electrons toward it. This one's going to pull toward it. They're pulling across this carbon in the middle, and neither one of them is stronger. I'm playing tug of war with an evenly balanced group. Nobody's going to win here. So even though I have polar bonds, the entire molecule is nonpolar because the dipoles canceled each other out. Now, that would not have happened had the shape of that molecule not been linear. They were pulling diametrically opposed to one another. And so it's important to look at the geometry and know the direction in which a dipole is pulling. And that's where we come into something known as vector notation. So what we're going to do is once we have a Lewis structure and we have a geometry for that structure, we try to represent the geometry, we're then going to represent polar bonds with arrows or vectors that point in the direction of the more negative pole. Okay, and then you put a plus sign at the positive pole. Okay, so it's going to look like this. So this will be the negative end down here, this will be the positive end down here, the partial negative, so remember the delta, and partial positive. Now, if the vectors are pointing exactly opposite one another, diametrically opposed as they were in carbon dioxide, then they cancel. But if the vectors point in the direction of an atom with a partial negative charge, you will get a dipole moment. You end up getting a dipole for that, and then you have a polar molecule. So if you've taken physics and you've looked at vectors in physics, it's very similar to that idea. We're going to add them up. So now let's look at water. Okay, now if we look at the Lewis structure for water, remember it looked like this, and I've got lone pairs here and here, and I've got a hydrogen. It looks a lot like carbon dioxide, right? And it's like, oh, I've got a hydrogen and a hydrogen. They're diametrically opposed. They're going to pull on each other. I've got two lone pairs. They're diametrically opposed. They're going to pull on each other. Everything cancels out, and it's nonpolar. Okay, you could not be further from the truth for water. Water is one of, it's a very polar substance. Why is it polar? Well, because the difference in the electronegativity between oxygen and hydrogen is 1.4. Okay, 1.4 and 1.4. And they are not opposite each other. They are not 180 degrees apart because of those two lone pairs up there that have shoved them downward. And so they're actually 109.5 degrees or so apart. Okay, and so what's happening is we have this bent structure. Here's the center. I've got one, and you can imagine it, with the oxygen and the hydrogens lying in the plane of the paper in a bent motion. Okay, this one's pulling down this way, this one's pulling down this way. What happens? There's a net movement now. I'm sorry, I've got them going the wrong way. So the electrons are pulling toward the oxygen. It's the more electronegative. So as you see here, down at the bottom, let's see. Let's get the eraser out and erase the ones we don't want. So, okay. So just so we don't confuse anything there. All right, now we are looking at the two vectors that are shown here. So the negatives toward the oxygen, the positive down toward the hydrogen. There's a net pull. If I add these two vectors together, I'm going to get a net movement in this direction. So this becomes a polar molecule. They don't cancel each other. Table 10.3 shows you some of the common cases of adding dipole moments and figuring out whether a molecule is polar or nonpolar. Okay, so nonpolar when you have 2 or 3 identical bonds pulling, or if you have all 4. So when you have the electron geometry being the same as the molecular geometry, as long as all the bonds are equal, it's nonpolar. But if you have any of those intermediate cases with lone pairs, those are usually going to be polar. And then again, for all of these nonpolar cases, that only is presuming that the bonds are equal. Okay. So if we go back to the idea of oil and water not mixing, well, we've already determined that water molecules are polar. They're very polar. So what does that tell us then about oil? Well, the molecules that compose oil are probably different, and they are. If we look at oil, it varies from one oil to another, but in general, oil molecules tend to be nonpolar. Now, like dissolves like charges repel, though. So polar molecules interact strongly with other polar molecules, like and like. The positive end of one molecule in a polar molecule is attracted to the negative end of the other. It's like putting a lot of little magnets together, and they're going to line themselves up. So polar molecules interact with other polar molecules. But if I mix polar and nonpolar molecules, it's kind of like putting magnets together with non-magnetic particles. So you may have done there's a classic experiment where you take iron fortified breakfast cereal, such as Special K, and you grind it up. You might even, get it a little bit wet, mix it up, and then you take a strong bar magnet and put it in there, and you end up pulling out little pieces of iron filings. That's actually how they fortify cereal with iron. They put iron filings in it, and you can separate it out. Well, that's because the iron is a magnetic particle. It's attracted to the magnet, but the other parts of the cereal are non-magnetic. They're not going to stick. Same thing here. Nonpolar molecules are like the rest of the cereal. They're not going to stick to your magnet. They're not going to be attracted to polar water. So the magnetic particles, which are the water molecules, clump together, and they shove out the non-magnetic ones that are in the oil and separate them into a distinct region. Similarly, polar water molecules attract each other, so they magnet themselves together, and they form regions that are very hard for nonpolar oil molecules to get into. Okay, so if we look at attraction over here, all of these beads, they look like they're all marbles, but these are actually magnetized marbles, and you can see how they're all sticking together and they've kind of clumped together. These are just standard glass marbles, and they're just lying here. They've been pushed out. So this would be like the water sticking together. This would be like the oil. Okay, and so you can see here they're showing oil molecules and water molecules separating out. Another interesting aspect that you can look at polarity is how soap works. So when you eat greasy food, so you're eating a greasy cheeseburger, you're eating potato chips, your hands get coated with grease and oil. And if you just try to go rinse them off with water, you still have beads of water on your hand still feels greasy. But you throw a little soap in there, the grease goes away. So how does that work? Well, it works because of a really interesting property of soap. Okay, so we've established that water molecules are polar, grease and oil are nonpolar. So if you're just trying to use water to wash grease off your hands, they repel each other. That's not going to do anything. Soap works to make those two come together. And that's because soap has a polar end and a nonpolar end. That's what's incredible about it. It's got both polar and nonpolar. So you've got this polar end that can interact with water. You've got this long nonpolar tail that interacts with the grease. And so what happens is the polar head of the soap molecule, well, let's start with the nonpolar. The nonpolar end comes in and attaches the grease and oil to it. So an oil comes in, it lines itself up with this nonpolar tail, and it forms what's known as a micelle. And there's a really fascinating video I'll try to remember to post that kind of relates that. Okay, so the oil sticks to this nonpolar end, And then this polar end comes over here and interacts with the water molecule and attaches itself. Well, the tail has the oil on it, and now when you rinse that soap off your hands, okay, the water is carrying the soap molecule away, and the oil is going along as a hitchhiker on that nonpolar tail of the soap. So soap basically just allows water and grease to mix. It just hooks them up at different ends and then carries them both away. Really interesting with soap. So that wraps up chapter 10. And the next chapter we'll look into, we're going to skip over 11 and 12 for the moment. We're going to go to chapter 13 and then come back and pick up 11 and 12.